Welcome back, everyone. We are starting a new unit 3A on bonding. In this unit, we will introduce ionic and metallic bonding. In this first lesson, we are going to learn how to draw Lewis dot diagrams of atoms and of ions. One thing to note is that Lewis dot diagrams are also known as Lewis dot structures or electron dot structures. They can be abbreviated LDDs. Please note that these are all referring to the same thing. In this video, we will use this term, Lewis dot diagrams. So what is it? It's a diagram that shows the valence electrons of an atom as dots. So they're represented as dots around the element's symbol. Now there are rules to drawing these. The first one is that no side has more than 2 dots, because each orbital can only hold 2 electrons. Rule number 2, when filling the sides of the element symbol, each side gets 1 dot before doubling up. Now we have to review some exceptions to the octet rule. For this, I have put here hydrogen and helium are the exceptions to the octet rule. The reason that these two are listed here is because these two only have 1 shell. And since they only have 1 shell, that 1 shell can only hold 2 electrons. So in no way will it ever have 8 electrons. It cannot hold 8 electrons. Its one and only shell can only hold a maximum of 2 electrons. Now, let's take an example from the periodic table and look at oxygen. How would this Lewis dot diagram look? Well, if we look at oxygen on the periodic table, we see it, and we gotta go to the last number of the electron configuration to know the number of valence electrons. Oxygen has 6 valence electrons. Now that means that oxygen is going to have 6 valence electrons around the symbol. We have the symbol here, and so we're going to draw 6 dots around it. Here's the first one, the second one, third one, and fourth. Now I'm going to stop here for a second. See how we are applying rule number 2, where each side received a dot before we started doubling up. Now we have no other choice but to double up because we have no more sides. There's only 4 sides, and they are already occupied by 1 valence electron. So we have no other choice than to start doubling up at this point. So now this side is doubled up, and this side is doubled up. At this point, we are done with oxygen. Oxygen has 6 dots around it. 1, 2, 3, 4, 5, and 6. Okay, so that is the Lewis dot diagram of oxygen atom. Now, let's go back to rule number 2. We applied it in the example that we just saw. Here's an example where it is not applied. Remember, rule number 2 talks about each side getting only 1 dot before you start doubling up. Now, the reason for this rule is because electrons repel one another. So electrons, which are represented by dots in Lewis dot diagrams, have a -1 charge. Electrons do not want to be next to one another. They are repelling one another. So we want to put them as far from one another as we can until we have to start doubling up on the sides. So here we have an example where rule number 2 is not being followed. Here we have 2 electrons being doubled up on 2 sides. And there is a side that is completely unoccupied. So this is a big no, because we can use this space that is blank over here. So this Lewis dot diagram of nitrogen atom is correct. All four sides are used, and only one side is doubled up because we have no other choice than to double up on that fifth valence electron. Okay, so here we have the Lewis dot diagrams of the first 20 elements of the periodic table. Now, if you look closely, these are all in groups. Let's label it. This is from group 1. This is from group 2. This is from group 13. This is from group 14. This is from group 15, 16, 17, and 18. Remember, we skipped transition metals because the valence electrons down a group vary. So we skipped over those and we went from 2 straight to 13. Now, one thing to note, a common mistake that I see from time to time is for helium. Helium, although it's in group 18, it does not have 8 valence electrons. It only has 1 shell, and it can only hold a maximum of 2 electrons. Helium has 2 protons, so the atom has 2 electrons. Remember, atom refers to neutral, so the number of protons are equal to the number of electrons. Now, although it's in group 18, it only has 2 dots. The common mistake is because it's automatically in group 18, many people think, okay, right away, 8 dots. Remember, helium is one of the exceptions to the octet, so don't get tricked up. Don't forget the exceptions. Now, going back to the octet rule, we talked about how the octet rule, it tells us that atoms want a full outer shell. A full outer shell means 8 electrons. Now, how do atoms that don't have 8 electrons on their outer shell get 8 electrons in their outer shell? Atoms will lose or gain valence electrons to make their outer shell full with 8 valence electrons. Now, the way they do this is by bonding with other atoms. And now when an atom loses or gains an electron, it is no longer an atom, it is now an ion. So let's take a look at that. When we have a positively charged ion, that is called cation. When we have a positively charged ion, that means that electrons were lost. The elements that tend to lose electrons are metals. So metals are the ones that form the cations. Here we have an example. Group 1 alkali metals, like sodium, would form a cation. Now, let's talk about the radius, the atom size and how it changes. So for a cation, if it's a positive ion, it's losing an electron, that means that it's getting smaller. So the positive ion, cation, is smaller compared to its parent atom since it loses an electron shell. The sodium atom is what refers to the parent radius. Okay, So parent atom or parent radius is referring to how the atom was in its regular state, in its ground state, how you see it on the periodic table. That's what it's referring to. Now, the cation radius is after it loses its electron. So for instance, sodium was a 2-8-1. So we see on the first orbital it has 2 electrons. The second shell it has 8 electrons. The third shell has 1 electron. Then when it loses that electron, it only has 2 shells that are occupied. So the first one still has 2 and the second one still has 8. It only lost that 1 valence electron, so the one on the last shell. So since it lost that last valence electron, it now is only occupying the 2 shells it has. So now the atomic radius is smaller. So the cation radius is smaller than the parent radius. So here we have the new electron configuration of sodium ion is 2-8. While over here, the sodium atom's configuration was 2-8-1. Here we have 3 orbitals, while over here we have only 2 orbitals. Let's go to the next ion we have. These are called anions, and they're formed when atoms gain electrons. Since it's gaining an electron, let's go back to the charge. An electron has a negative charge, a -1 charge. So if it's gaining an electron, then it's going to be a negatively charged ion. Now, the types of elements that gain electrons are nonmetals. And so nonmetals are the ones that form anions. Now, one thing to know differently from cations, for anions, when you name the ion, the name changes. What do I mean? The suffix or the ending of the word will change to "ide." So, an example of this, real quick. Oxygen is a nonmetal. Oxygen, when it gains electrons and becomes an anion, will no longer be called oxygen, it will be called oxide. So that is referring to the last bulletin point. Okay, now let's talk about the size. The anion radius versus the parent radius. So once again, the parent radius is talking about the neutral state of that atom. So I'm just going to label it here, parent atom. And this is over here, the anion radius, or the anion atom. And the way I know that this is it is because here we have a charge, a -1 charge. So the anion charge ion is bigger compared to its parent atom since electrons are gained. Okay, so there's nothing new here to remember. I want you to think of a book bag. When you start putting things into your book bag, right? Your water bottle, your gym clothes, etc. Whatever you put in your book bag, you see that your book bag starts to get stuffed. It starts to get big. Same thing is happening here. If an atom is gaining electrons, it's becoming bigger. And vice versa, if we're taking out things from our book bag. Let's say when we come back home and we're taking out the dirty gym clothes, you're taking out the food containers to wash. As you start taking out things from that book bag, the book bag gets smaller. So that can refer to a cation. a cation means that it lost electrons. So if it's losing electrons, you're taking away electrons from that atom. It's becoming smaller. Okay? So you can compare this to stuffing your book bag or taking out things from your book bag. In this case, we're talking about an anion. So once again, an anion, you're gaining electrons. So you're putting things in. So this could be referred to in your book bag. You start putting things into your book bag, it starts to get big. Same thing is happening here. This chloride is gaining an electron, it gets bigger in size. Now let's go to a little bit of practice. Here I want you to pause and take a second to try to do these problems yourself. And now the Lewis dot diagram for these ions, we have to draw the brackets, and also we have to draw the dots, if there's any dots around it. So here is how this would look like. The Lewis dot diagrams of these ions would look like this. So magnesium has a positive 2 charge, meaning that it lost 2 electrons. Magnesium initially had 2 valence electrons, but it had to lose those 2 valence electrons, so it no longer has any dots around it. And plus, this is a cation. Now, chloride has a negative 1 charge, meaning that it gained 1 electron. And it has 8 dots around it. Take a look at how the name changed. It is no longer chlorine because it's no longer an atom. It is now an anion, and the name is chloride ion. Now take a look at the next one, fluorine. It has a negative 1 charge, so that is telling me that it is an anion because it's a negatively charged ion. It is no longer called fluorine, it is now called fluoride ion. And since it has a negative 1 charge, it means that it gained 1 electron. And here we have aluminum that has a positive 3 charge, which means that it lost 3 electrons. And it is a cation because there's a positive charge. Same thing for lithium, it's a cation. And the positive one is telling me that it lost 1 electron. Okay, a couple of things I want to note before we move on. Take a look at the cations. Do we see anything that's similar between these cations, the Lewis dot diagram of these cations? One thing we could note is that they all have 0 dots around it. So they don't have any dots around them. And now another thing we can note is that the anions, on the other hand, have 8 dots around them. One last thing is that the name for the anion changed, right? The suffix became IDE. But for the cations, it will be the same. So aluminum has not changed, even though it is now a cation. It is still aluminum, so it would be aluminum ion. Lithium's name will not change as well. It would be lithium ion. And magnesium, the name didn't change. It will be magnesium ion. Okay. So now let's compare the Lewis dot diagram of an atom and of an ion. Here we have lithium as an example that we're going to use. Lithium is located at the left side of the staircase. So this is a metal. Lithium has 3 protons, and it has a total of 3 electrons. Okay, that is in its neutral state, that is in its ground state, and its electron configuration is 2-1. That's how we know that it has 3 electrons. How do we draw the Lewis dot diagram of lithium? We see that it only has 1 valence electron, so it's going to look like this. The LDT of the atom for this will be lithium, the symbol, with 1 dot. Okay. And now, in order for lithium to become like one of the noble gases, it's going to lose an electron. So over here, as an atom, it has an electron configuration of 2-1. After it loses 1 electron, the LDT of the ion will be lithium with no dots around it because it lost that valence electron. It will have brackets and it will have a +1. That represents its charge, and it also is coming from over here on the top right side of its box on the periodic table. And now its new electron configuration is just going to be 2. Now if you look in group 18, which noble gas has an electron configuration of 2? That is helium. So noble gas electron configuration like helium. Helium has an electron configuration of just 2 as well. Now, how did this charge come to be the charge of lithium? Instead of looking at this top right corner, let's do the math. So lithium has 3 protons. That will never change because if you change the number of protons, you're changing the identity of the atom. So the lithium ion still has 3 protons. It no longer has 3 electrons. It only has 2 electrons now because it lost 1. So now let's get the net charge of this doing a little bit of math. So it has 3 protons. Each proton has a charge of +1 plus 2 electrons, and each electron has a -1 charge. So we do 3 times 1, which is 3, plus 2 times -1, which is a -2. Add it all together, we get a +1. That is how we get the net charge of lithium using the number of protons and the number of electrons. Okay. So from here, from the atom to the ion, what happened is that lithium lost 1 electron. And now it has a noble gas electron configuration like helium. Okay? Let's look at another example. Phosphorus. Phosphorus, now this is on the other side of the periodic table. This is a nonmetal. Now, phosphorus as a nonmetal, it will gain electrons. How many electrons? We will find out in a bit. So phosphorus has 15 protons and 15 electrons in its neutral state. What is the Lewis dot diagram of phosphorus atom? We're going to look at the valence electrons, which is 5. So that means that we're going to draw the symbol and we're going to put 5 electron dots that are going to be represented as dots around it. So here we have the Lewis dot diagram of the phosphorus atom. Now, phosphorus is going to gain electrons in order to have 8 valence electrons. How many electrons does it need? Well, it has 5, and if the goal is to have 8, it's going to gain 3 electrons. So the LDD for phosphorus is going to be like this. It's going to have 8 dots around it after it gains 3 electrons. Brackets, do not forget your brackets. And a charge of 3 minus. And that is also the first charge that we see on the top right. Now the reason that it's 3 minus, it gained 3 electrons, and each electron is a -1 charge. Now the electron configuration for phosphorus atom, we get it from the electron configuration that is shown on the periodic table. It's 2, 8, 5. Now over here, it is no longer that. It is now 2, 8, 8. Now, this electron configuration is similar to one of the noble gases. If you look on the periodic table, which noble gas electron configuration is 288? If you found it, you know that it is argon. Ar. So now it is like one of the noble gases. It has 8 valence electrons, but it is not one of the noble gases. Let's not get that confused. It's still phosphorus, but now it's an ion. So now it is not named phosphorus anymore. Its new name is now phosphide ion. Okay, now going back to how we make sense of this -3 charge, instead of looking at just that number on the top right on the periodic table, let's do the math. Phosphorus has 15 protons. It has 15 protons, and it no longer has 15 electrons, so we got to count it up. So 2 plus 8, we got 10, plus 8, we got 18. So now it has 18 electrons. Let's do the math. 15 times the charge of each proton, which is +1, plus 18 times the charge of each electron, which is a -1. Add this up. Here we got 15. Here we got -18, and that gives us -3 as the net charge. And that is why phosphide ion has a -3 charge. Same thing over here for the atoms. I didn't do it for lithium, but let me do it for phosphorus atom. Over here, phosphorus atom has 15 protons. That never changes. Once again, if you change the number of protons, you are changing the identity of an element. Please do not do it. And we get the number of electrons from the electron configuration. So if we're talking about an atom, whatever we see on the periodic table, that is what it refers to. And we have 15 electrons. 15 times the charge of each proton, which is +1, plus 15 times the charge of each electron, which is -1, +15, plus -15 is going to give me 0. And that is why you do not see a charge in any of the atoms, but in this example, phosphorus, you don't see a charge. Okay? At this point, we have reached the end of this lesson. Here's a quick summary of what we did discuss today. We talked about metals and how they tend to lose electrons and form cations. We said how the dot structures of cations show brackets and a charge, but no dots. You don't see any valence electrons around it. For nonmetals, they are the ones that gain electrons and form anions. The dot structures for anions show brackets and a charge and the 8 valence electrons.